All right. We talked about a couple of flows. One was a flow between two parallel plates, and the plates held fixed with a fluid flowing under a pressure gradient between these two plates. That's the pressure gradient that's being maintained from outside, and there is this viscous fluid which is flowing between, and we found that there is a parabolic profile. And if this distance over between the plates is d, and that's that, there is going to be some mean velocity of flow. The velocity profile is going to be parabolic profile, as I said. If this is the x direction and that's the y direction, and the flow is in the x direction, Vx is going to be some, let's say, some u times y into y minus d. So u equal to some Vx is some u into y minus d, where this u which we calculated was determined by the delta p over L and the shear viscosity coefficient, and there were some factors or so on and so forth. So the velocity scale was set by the pressure gradient that I was maintaining, and the flow profile is given by that. It's a steady state flow, and that's a solution of Navier-Stokes equation. The Reynolds number for this flow is the distance between the, so the Reynolds number for the flow is the velocity scale that appears over here, and times the d square has to appear somewhere or other in this formula. And so it is going to be the Reynolds, that would be the controller of what kind of flow I would have. So the other case which we did is a question of two infinite plates enclosing the fluid, except that now it's a question of having the fluid heated from below. So you heat this fluid from below, keep this at a temperature T1, this at a temperature of T2. There is a distance d between these two over here, and the issue over here, the controller of what kind of dynamics I'm going to get, was this quantity alpha delta T g d cubed divided by the thermal diffusivity times the viscosity. So all right. So the issue over here was what we could show was that the steady state profile, this is a possible steady state profile. It's a bona fide solution of Navier-Stokes equation. But then as we have been saying, that Navier-Stokes equation is a linear, is a nonlinear equation in the velocity. So that's, we are talking about incompressible flow plus any f that I may have outside, and divergence v equal to 0. If I have a temperature field that I have to talk about, then there is the question of del del t plus v dot del on t that's equal to the thermal diffusivity kappa times delta T, and if it is a question of heating and so on, this has to be judiciously used. As we saw yesterday. So the point was, all right, so there is this steady flow over here, and the point which I just mentioned but did not, would certainly not be able to demonstrate at all, that you can show that this flow becomes unstable at about a Reynolds number of 6 times 10 to the power 3. And the instability which develops makes it is still axisymmetric flow with a wavy pattern in the x direction. So it's an axisymmetric flow with a wavy pattern in the x direction. That's what you get when you cross a Reynolds number of about 6 to the power 6 times 10 to the power 3. The wavy pattern becomes more complicated as you go on increasing the Reynolds number. If it's more and more complicated, if you hit 10 to the power 10, certainly maybe a little even below that. Sorry, that's not even a question of, there's 10 to the power 3, there's a question of 10 to the power 5 or 10 to the power 6, where you can discern no regular pattern in the velocity field. So that's just a fact. Only this is what I have been, what I have shown you, and thereafter this is well, just you have to take my word for it. Over here, the situation, what we have done is slightly better in the sense that if the Rayleigh number is very low, there is this steady state which is V equal to 0, no movement of the fluid at all, and heat being simply conducted from the bottom plate to the top plate. So this is a solution of the system over here with the pressure sitting at the hydrostatic pressure being the solution of divergence P rho over rho naught equal to minus there is the external force, which is the force of gravity, so it is minus g vector. So that there is some rho 0, whatever is the relevant rho 0. So V is equal to 0, T equal to T1 minus this, and that's a solution of the equations we have. What we yesterday during the main lecture, I gave a qualitative argument why this is not going to be sustainable. It should never have been sustainable, mind you. I mean, this is one thing which you have to appreciate, that this is a hydrostatically unstable situation. There was no reason to believe that this state should be stable. It's dynamics which stabilizes it. There is this question of the buoyancy force that is released by the heating from below is effectively countered by two dynamical quantities, the viscosity and the thermal diffusivity. So dynamics can lead to stabilization, and this is it is dynamics which allows you to have this state over here as a solution of the relevant fluid dynamics equations. Then the argument that we gave in class yesterday was that if this Rayleigh number becomes sufficiently big, then the heat flow, this state of affairs would not be permissible. The hot fluid would start physically rising and initiate a flow. In the evening, we calculated this actually and found that the critical Rayleigh number for doing for this onset is 27 pi 4 over 4. If you make some what is called ideal fluid. Ideal fluid meaning something with which you can manipulate boundary conditions. That's what really ideal fluid means. They don't exist, but you manipulate, you say that with ideal fluid, boundary conditions are such that I can play games easily. And that's what we did yesterday. Instead of having real viscous boundary conditions on the two plates over here, we had these ideal fluid boundary conditions, which are also known, if you want to be a little more, make this sound better than it is, you can say stress-free boundary conditions. And under those, as we saw, that it's workable, it works out easily, and the critical number that you find for this is 27 pi 4 over 4, as opposed to the real answer, which is 1708. So get about 1/3, a little better than somewhere between 1/3 and half. But this I wouldn't be able to work out on the board, whereas this I could in a few minutes. So there is something to be said about these manipulating boundary conditions. All right. So then this is the first instability, a state with V equal to 0 going over to a state which, if you now, I mean, this just tells you that this state has become unstable. It does not tell you what is the stable state. Then you have to further, then you have to go actually solve, once again try another kind of solution which you expect. So maybe some kind of a roll pattern, but all that you know, what the kind of instability, this V which we postulated to look at was of the form e to the power I k1x plus k2y, infinite plates in the xy direction, and some fz and some function of t over here. So we had these essentially periodic structure because of the infinite extent in the xy direction. We asked for a periodic structure, and we found that at the onset over here there is all that one can say is that k1 square plus k2 square has to be pi square over 2. So infinite degeneracy. I could have any pattern whatsoever with k1, the different choices for k1 and k2 gives different patterns, and I could have any pattern whatsoever. As I said, that reality is that the pattern, if you see it from the top, is a hexagonal pattern, and that's what happens if you do experiments. That's what happens if you look at the street or in the pen. And so that's an open issue, but anyway, be that what it may, the solution is a steady convective state. So that's you work a little harder and you get a steady convection pattern. You increase the Rayleigh number some more. So increase the Rayleigh number, and then in this direction, suppose it were a cylindrical roll that we were talking about, this axis starts to wiggle. So this axis starts to wiggle. Once again, I mean, you ask the question, you do exactly the kind of calculation we did last evening, that take the steady state, ask if there is if a perturbation is going to grow over there, and sure enough, a perturbation which has a undulation of the axis grows. And if you go on increasing the Rayleigh number still more, you find a more complicated pattern. And when the Rayleigh number is of the, so this was 2000 where you set it up, so 10 to the power, so 10 to the power 3 times this 17, the critical value. So roughly at about this, once again, it has become extremely complicated flow pattern. So this is the generic situation. You start with something which looks nice and tackleable. You have a velocity field which you can write down in principle, visualize it, and if you can't even write down it, you can visualize it. It seems like some function that in principle you should have been able to write down. But then there is a control parameter in the system, the control parameter being the Reynolds number over here and the Rayleigh number over here. So there is a control parameter which, if you change, does make the business more and more complicated. And eventually you reach a situation which, for all practical purposes, seems to be a domain where the flow is more or less random. That is, more or less random meaning that if I look at the velocity, if I look at some component, let's say the x component of the velocity as a function of, let's say, as a function of r and t, and fix this, fix the position r and plot it against t, then this function over here will be like the functions which everybody else has been drawing in these set of lectures, which looks with no perceivable pattern in them, which can be called random function, changes randomly at time, which means that if I do a Fourier transform and look at the Fourier transform of this, then a periodic thing. So if I look at the Fourier transform v omega, if it were nice and periodic, the Fourier transform would be a single frequency. It would be a single peak at the frequency at which the motion, for example, this undulating pattern over here, or the first instability of the Heisenberg problem over there, would just give you a single peak in the frequency spectrum. But then things start becoming problematic. You have at in omega 1 some the incommensurate with omega 0 some component appearing, and then eventually when it is of this variety, you have this you have a continuous distribution of frequencies in your spectrum. So the time series is such that there is no discernible preference for a set of frequencies, all frequencies present, which essentially causes a problem. So similarly, if you were to take a time snapshot and look at Vx, let's say, as a function of x and t. So this is fixed time. You take a snapshot, and the result is once again something which is. So this is what this is the picture-wise meaning of what is fully developed turbulence. So the meaning being that the flow looks like a random, the velocity field looks like a random function of both coordinates and time. So we are, I mean, in the process, what we are going to do is jump from the safe side where we can give some demonstrations and skip this whole area, which is totally unreachable by any analytic means. It is all computational work over here. There is no way in which you can, that is, starting with these partial differential equations, getting any one of these states analytically is virtually impossible, but it's reasonably straightforward, reasonably all right numerically. Then comes this part over here. So here the complication has become obviously immense, but as you have been seeing over this entire week, there is a different way of bringing some method into this region over here, where it has become a fully random flow, and therefore there should be some way of this thing actually connecting to the kind of discussions that have been going on in the other lectures. And also, so all right, so maybe, I mean, there are issues over here which can be addressed, which are issues of random flow. Question is, what one has to be absolutely honest about is it of any use? You see, that if the practical fluid dynamics, which engineers do, solves the Navier-Stokes equation, heat conduction equation, everything numerically in whatever region of Reynolds number, Rayleigh number that you may have, and get confident answers so that your plane doesn't crash. So there is no, there is a certain amount of futility in talking about this part over here. I mean, so this is something which one has to keep in the back of one's mind. But then comes the question of then, I mean, why should there be, I mean, why should I not stop? And nobody does, is one answer. And then the point is, all right, I mean, there is some certain things which the physics people can probably say. So but for the physics people to say something, the attitude has to be somewhat different. You have to sort of take a point of view that you are going to look at something which may not be tremendously relevant for practical purposes, but it can have a certain other kind of utility, and therefore the thing is worth looking at. So why? So what is the attitude that one is going to take on this? So why would one? So, for example, I mean, where would the physics person have advantage over, let's say, the practical world? The point with the practical world is that if you are going to rely entirely on numerics, every time you have a different fluid, you have to redo the calculation. What kind of viscosity? The viscosity of the fluid. What kind of external forces are troubling the fluid? And if it is heat conduction as well, what kind of thermal conductivity? These would be issues which would have to be very important, and every time these issues change, you would have to do the numerics all over again. Question is that can I focus on issues which are universal in the sense, so universal in the sense that they are independent of nature of fluid and of any external influence. Meanwhile, I mean, if you have any doubts about whether turbulence is a useful thing in life, the answer is they're very simple, because if I were to take a glass which is, let's say, roughly 10 centimeters, 10 centimeters high, and have it filled with water, and put a blob of sugar or salt over here, and wait for it to mix completely through the diffusive process, then the time for dissolution, time for mixing, let's say dissolution may bring in chemistry in it, why take unnecessary risks. So T mixing is going to be d square over the relevant diffusion coefficient. These diffusion coefficients are typically of the order of 10 to the power minus 2 in good old CGS. So it is 10 to the power 2, 10 to the power minus 2, that many seconds. So that's 10 to the power 4 seconds. That's of the order of hours. So if this lump of sugar is going to, if you are going to take a natural processes act and do the mixing, it's going to take a very long time, but you stir it up and make it turbulent. So you make this thing move with the fluid, and that increases the diffusion very much. So there is a turbulent diffusion which is much, much greater than the natural atomistic molecular diffusion, and as your experience is, that 10 to the power 4 seconds is brought down by the to maybe 10, let's say 10 to 100 seconds. So you have a tremendous increase in the dispersive, in these diffusive properties, and that is a very practical thing. So it is not that it is not worth studying. There is a question. There are issues. You see them every day, and so it's worth understanding. So all right. Very, very good. So now, that's why. But now, this universality has been always the key word for the physics people, and so you want to know. I mean, can I focus on something which is independent of the data? So all right. So now, what can I focus on? So you can say that, well, look at, so your claim is that V R of t is a random variable. So that's what we claimed. So the natural question that you should ask, given what you have been seeing over the last 5 days, is what is the probability distribution? Right? I mean, that should be the natural thing to go for. That if I tell you that fully developed turbulence means that the flow has become random, then it is you have to ask me that, all right, tell me what the distribution is. So whose distribution? Number one. Now, this thing you see is quite first there is inhomogeneity. So you want to get rid, you want to talk about a variable which is which is not affected by inhomogeneity. So that's a normal natural desire. So you, I mean, after all, you are trying to get to things, something which would have universal features in it, and so you don't want this issue of universality, inhomogeneity. So you say, all right, I will look at, say, some component alpha of V, I mean the V vector, but at x plus r minus, I will look at this difference over here. Now, this difference over here takes care, if you want to look at this difference, then that difference is dependent only on two neighboring points. So, point 1 over here, point 2 over here, and it is this r which is the difference between these two, and whatever inhomogeneity affects this also affects this, for example, if they are not too far away, and this is a candidate, V alpha x, this difference is a better candidate than V for the quantity whose probability distribution is going to be of use. So your natural thing would be to say, I have told you that V is a random variable. You say that, all right, give me its probability distribution. Then I say, all right, wait a minute, this inhomogeneity bothers me, so I'm going to look at this difference over here and then talk about the probability distribution. So the probability distribution that we are going to talk about is this of this quantity, which, to make it clearly a function of r, you look at this quantity at different x's, and so you sum over, let's say, this xi, the I equal to 1 to n, and divide by n, and this quantity is going to be your delta V alpha as a function of R. So very good. So I have removed the inhomogeneities, and I have got the delta V alpha as a function of R. So then you say that, all right, let's do a more, I guess, thought experiment. So that you imagine doing this, getting, there are all these getting time series for so you get a time series from for this delta V alpha as a function of t, run it for as long a time as you can take, as you want to take, and then you look at the same stretch of it. No, all right, sorry, let me draw something that it's going to look like, I mean, some thing or other which visually makes no sense to any of us, but it appears like. But now comes the important point. Take the same length of it at different points. Something I think Abhishek mentioned yesterday about how you should play with a time series, and one time series does the job for you if you are. So you take this and break into equal sized bands, and you ask the question that a particular value for this band over here, you ask the question that how many times does a particular value of delta V alpha occurs. So you have a point somewhere over here, you get a point somewhere over here, and then some here, and say something which looks like this. So this is the number of times a particular delta V alpha occurs. Then you take this band over here, and you start asking the same question, and you say, and you find, let's say, that this gives you a set of points like this. Then you look for this chap over here, same question, and you find that it gives you something like this. Same question over here. And now by this time you have got what I'm driving at, that here is a curve which looks like this. This is the probability divided out by the number of runs. And so P of delta V alpha against delta V alpha has given you this probability function. That's and the important statement is that this P of delta V alpha, just as it was independent of which cut of the time series did I take, is independent of fluid and forcing. And that is what one is interested in. So you have, I mean, as Anderson had once said about these high TC, the first thing that one has to know, the normal thing, couching it under the that you have to know the enemy. So it's over here, I mean, in a sort of same sort of thing. As it turns out, this would be the enemy. But you have to know what is it that you are up against, essentially. And what you are up against is getting this probability distribution. That is the holy grail. So, yeah. No. That's there isn't. There isn't. Huh. It is just, I mean, these bands are identical, let's say identical realizations of the same system. Of the width of the band, yeah. Unless I take the width probably as 10 to the power 6, which also works anyway. Okay. Chop out a little bit here and there. And as one makes R larger and larger. All right, so R larger, and that's I have not yet come to the scale. Now, as R gets larger and larger, obviously the correlation for some scale of R, the correlations would trivially would be, but then the point is that there is going to be over a short, very small length scale, as we'll see soon, small and large, that there is a certain growth in this, there is a characteristic growth of the correlation over a small length scale, and so one focuses more on that growth part rather than the very large R's. And already in that small enough growth part, there is a deviation from the Gaussian. I have not told you. I mean, I have just drawn for a given delta V R, I have drawn a distribution but I have not told you anything really about what happens as I change my R to small or big. So this is, let us say, for a representative R as yet. Huh? Yeah, I mean, but so the point, I mean, what I'm after is that this would be it. If I could tell you this, you would say that you are satisfied, I have given you and everything you wanted. The fact of the matter is that I can't give you this. I mean, that is, this is for P of delta V alpha for given R, and how with R taking on different values, small and big, is not something which one can construct. So all right, I mean, you can't construct, then you settle for, if you can't get the simply because now what you have been seeing in the other lectures, that this is what is being aimed at. You are trying to calculate this and succeeding in calculating this. The difficulty over here is the infinite number of variables that one has to contend with. You are talking about a set of partial differential equations which are coupled to each other, and therefore the technical difficulties of finding this has been extremely high. So all right, I mean, you say I can't get the probability distribution, but I'll give you the correlation functions. So why don't you settle for correlation functions? So now, which correlation functions? So I'll say delta V alpha to the power n, that correlation function. Now, that correlation function obviously does not settle the issue of the probability distribution, because you would like to know all correlation functions which are like, so this is at the same value of r, and you would presumably like to know also that what is, this is r1 raised to some power n, and this delta v alpha beta raised to some at r2 raised to some power m. All so quantities of this kind which would come and even you would have to give answers for. So, but so you take, say, all right, let me start with a much restricted goal, just one delta v of alpha r to the power n. Do I know anything about that? So, well, all right. So you say that, or forget the probability distribution, calculate moments. Moments, after all, the equations of motion should give you some ability for calculating moments. So you could be, you should have an answer for that. But then you find that that also is rather problematic. So you say, well, would you settle for n equal to 2? And then you say, all right, let's start with n equal to 2 and see if I can even get you that. So the whole business starts with then what would one call a calculational aspect of this, is that, all right, let me start with a very restricted goal. Am I competent to tell you what n equal to 2 is? So that's and all right, if you can this. But before we get into actually calculating, now what one thing you can easily see, that this n equal to 2, why focus on the n equal to 2? Because the n equal to 2 would have something to do with the energy. It is v squared, and so energy is a quantity which is quite practical, and therefore getting at the energy is something useful. So n equal to 2 starts out life in a sort of practical manner. All right, but now then let's look at some, before we get started with a calculation, you would have to answer questions about where should this calculation be done. What, in which, what kind of, let's go back and look at Navier-Stokes equation. So del V alpha del T plus V beta del beta V alpha is equal to minus del alpha P over rho plus nu del square V alpha plus, or no plus alpha for the time being. So that's where we are. And as you can see, question of getting a correlation function where just multiply by another v and take averages and get start going somewhere or other. But before we go anywhere, it's much more difficult, much more difficult actually. Now the point is that, does this random variable have a mean or not? It must. I mean, there was a flow, for example, the Poiseuille flow which we started out with, there was a nice tendency to flow from this side of the tube to that side, the plates to that side. So this V alpha is actually, you can write it as U alpha, which is the average value of this, plus a fluctuation which you write as a small alpha. So that would be the, so average value of u alpha, this is the pure fluctuation over here. So the average value of the fluctuation is 0. So similarly, the pressure that we have is, there is some average pressure plus there is some fluctuating pressure, which let's say is P alpha. So it's good to see what those means and fluctuations are doing. So you do a del del t of u alpha plus del del t of u alpha, that's the mean, that's just substituting this, and there would be a bunch of terms over here, u beta plus u beta del beta u alpha plus del beta u alpha equal to minus del alpha p0, call this some p0 over rho minus del alpha p prime over rho plus nu del square u alpha capital plus nu del square u alpha small. Take averages. Take averages, out goes this. So it is del u alpha t plus u beta del beta u alpha, that's a survivor. This into this is not a survivor because it is an average u beta is 0. This into this is not a survivor, but this into this is a survivor, plus average of u beta del beta u alpha equals that's a survivor, that's not a survivor, and that's a survivor. So minus del alpha p0 over rho plus nu del square u alpha. So the mean satisfies your standard Navier-Stokes equation, except that it does have a contribution from the fluctuating part. So there is this fluctuating part, one part of this which affects the mean flow, and there are, in literature you will find that you can sometimes get by making some statements, approximate ways of relating this mean to the relating this average to the mean flow in some form or other. Various these go by the name of Prandtl mixing, some various ways, mixing length hypothesis, that is the key word. There's Prandtl, there's Taylor, there is a whole lot of people associated with it. But so you make some statement of on this on some reasonable ground to get a picture of so this in terms of the mean flow velocity and some characteristic length and that. So all right, now what is the fluctuating part of it? Subtract this from this. That's going to tell you what the fluctuating part of this is. So the fluctuating part is going to be del u del alpha t plus, now I'm pardon? Pardon? Small u alpha. No, that the whole idea of turbulence is the u alpha as big as capital U alpha. Oh, notation. Sorry. Yeah. Right. What would you like? W. All right, W it is. Very good. sorry. As you wish. All right, W. Then, very good. So this plus the W beta times beta, that on W alpha equals, now, so I have picked up this chap over here. This chap is gone. This is gone. And there are the two terms which are left over there, which I will write, is minus del alpha p prime over rho minus plus nu del squared W alpha, and then three additional terms which are minus W beta del beta U alpha minus U beta del beta W alpha minus expectation value of W beta del beta. Incompressible, it's just a constant. So P0, I mean, actually rho could have been set equal to 1, just other, that would have been a, yeah. So that's it. Now look at this. Up to this part over here, this is the standard Navier-Stokes equation for the fluctuating quantity. Here you have some kind of interaction between the mean flow and the fluctuating flow. So these two terms over here are some kind of mean flow interaction between the mean flow and the fluctuating flow. And this is simply this term over here. Whatever mixing length approximation you do over there, you have to do the same thing over here. But this is a part where you see the mean flow and the fluctuating flow are interacting, and therefore you can see that there is going to be energy transfer from the mean flow to the fluctuating flow. So that is a term which one should keep in mind, as we'll come back later to say something about it. But it is this, if I think of this as a force term on the right hand side, then mind you, this is a term which is a fluctuating term over here, and the interaction between the bulk motion, the mean motion of the flow and the fluctuation, it provides essentially a kind of external drive for the fluctuating part, and that external drive is itself really a fluctuating drive. All right, so here is the mean flow, and we are not going to worry about it anymore. So we'll talk about this part of tacitly. The point would be that when I talk about this Navier-Stokes equation over here, I'm talking about the fluctuating part. I have dropped this extra forcing that comes from it comes from the coupling with the mean flow, and drop this, which is after all the averaged out effect. And there is this question, I think of Navier-Stokes equation as written over here as completely in terms of this fluctuating variable, fluctuating velocity. So in terms of the fluctuating velocity, now what do I do first? I look at the energy of this flow, and this is where I'm just going to make use of the result that we had obtained before, that del t of integral V alpha V alpha d3r by 2, that's the kinetic energy, that is equal to minus nu integral V del square V alpha d3r. The other two integrals which I will write, alright, now the other two integrals which we have, V beta V alpha d3r, that's equal to 0, and this is all for an incompressible fluid, mind you, it is divergence V alpha equal to 0, divergence V equal to 0. It's the incompressibility which makes these integrals 0, so V alpha del alpha d3r. So in this energy budget, these terms play no role. The only role is played by the kinetic energy, which says that you are going to dissipate the energy away, and so the total eventually after a long time the total kinetic energy would have to go to 0, and that would mean the motion would have to stop. So if I want a maintained turbulence, so I want a situation where there is a steady state in this system, that is steady state so far as this energy is concerned, then I better have external force. I need to have external force over here with F alpha V alpha d3r, and the steady state regarding the energy, total energy of the system would have to mean that the rate at which you are supplying energy, this is the input of energy, and this is the dissipation of energy, and these would have to be at the they would have to equal each other, and so the rate for this steady situation, rate of input, will be equal to rate of dissipation, and this is generally written as epsilon. So epsilon is a quantity which appears repeatedly and see all over the turbulence literature, and that is this input and dissipation rate. So all right, but then you say, all right, I mean that's it. I mean what do I have to, why do I need to worry about these chaps over here? What's their role in the whole process? I have integrated things out, removed them, they have become 0 for this incompressible flow. So one can sort of happily get rid of them. So now the question is, well, all right, I mean that why is it not so? And for that, one now needs to talk about, for the first time, what are the scales in this problem. So given this picture over here, now I'm in a position to talk about scales. Here is energy being driven into the system. So back to this analogy of, back to the example of stirring up your coffee cup. And so you have this stirrer and stir up your coffee over here. You are supplying energy, obviously, by stirring it up. And supplying at what scale? The scale which is the size of the, which is essentially the system size, capital L. So I have a system size and some capital L, which is system size, and where this input is effective is at length scales of L, which is very large. Where is this taking place? This dissipation. Dissipation is taking place due to this molecular viscosity. And as is proportional to the gradient of velocity square. So this obviously has to be over extremely small length scales where the gradient of V has become significant, and also where nu is a player. I mean, nu is not a player in the bulk of a fluid, never is. But come to small length scales where the molecular viscosity is operative, let's say a length scale of small l, that's where it is taking, it's come into action, and therefore that's where it dissipates out this energy. So you have length scale, two length scales in this problem, a length scale which is large and a length scale which is small. Now I have to determine what these length scales are. Well, what determines the length scales? The length scale small l. So I have a rate of dissipation or rate of production of energy. So there is a rate of dissipation of energy, which is this epsilon over here. There is your molecular viscosity, which is nu. And so this small length scale which you have over here, L has to be constructed, L is to be constructed from epsilon and nu. So I need to know, what do I do? Dimensional analysis. So this is, I mean, most of these things would go by dimensional analysis, which is a great thing. So what is the dimension of this rate? This is energy per unit mass. So energy per unit mass is L square over kinetic energy per unit mass is L square over T square. Rate, so that is 1 over T. So this is L square over T cubed. What is viscosity? So this one is L square over T cubed, and this one is L square over T. So I have to get rid of the time to form this length scale over here. I have to get rid of T. So I need nu cubed. So I do epsilon by nu cubed. So if I do epsilon, I do nu cubed by epsilon. So I do nu cubed by epsilon, then it is L to the power 6 divided by L square, and so this is raised to the power 1/4. So I have a small length scale in the problem where nu is operative, it's operative at a small scale, and that's it. What about the input? The input is at a scale which is of the system size. What are the energies over, what are the velocities over there? At the system size, the velocities are more or less the mean velocity of the system. So at these large scales, it is what you are seeing is going to be at large length scales essentially the mean velocity which we talked about, this u, that is the operative velocity at those length scales. And out of this capital L and U, I have to form a rate of input which has to be the same as the rate of dissipation. So it's still the same epsilon, and now epsilon as it is L square over T cubed over here. The velocity is L by T, so I have to remove the T cube. So it is going to be U cubed. So if I take U cubed and divided by L, then I form this epsilon once again. So the from the one side of this, so there is this decreasing length scale on the, this is a sort of anti common sense picture. Here is my length scale which is big L, and here is my length scale which is small l. Over here I have relation L is in terms of U cubed over epsilon, and here is a small l. So the first thing I want to know that how far away are these scales from each other. So I need to form the ratio. So I need to form the ratio of capital L by small l. So capital L by small l is going to be U cubed over epsilon, U cubed over epsilon divided by this character over here, which is epsilon to the 1/4 divided by nu to the power 3/4. All right. So which is nu to the power 3/4, which is nu to the power 3/4. So epsilon to the power 3/4 divided by U cubed epsilon 3/4 by nu 3/4. Once again, let me go back and use that, which is this is looking a little. What happened? Got something wrong. This is okay, right? I mean, U cubed over L has to be right. So L is U cubed over epsilon. So that's all right. Now this is L, small l over here. So that's nu to the power 3/4. And then I have over here epsilon to the power 1/4. So this should have been 3/4 over here. So better now. So this is U to the power, so epsilon to the power 3/4 is U. So this is just wait and get it. So epsilon is 3/4. I want the whole answer in ratio in terms of U, capital L and nu. So it is going to be U to the power 3, epsilon to the power 3/4 is L to the power 3/4 over here divided by U to the power 9/4, and this is nu to the power 3/4, which is equal to UL over nu to the power 3/4. But UL by nu is our great old friend Reynolds number. So this ratio L over here is Reynolds number, to the power 3/4. And now I am in business. So this ratio, if I am at the large Reynolds number flow, which I said is the place where turbulence occurs, so if you are looking at a Reynolds number of the order of 10 to the power 6, let's 10 to the power 8 for to make life simple, then you are looking at a ratio of L over L, which is like 10 to the power 6. So 6 orders of magnitude between here and over here. And therefore, I have in between over here a range of scales where this R, L is much greater than R and much greater than small l, and in this range you see life is completely oblivious of the small scales over here and the large scales over here. If you are sitting in this at scales which are of the region of the size of R, which is so very different, then you are not bothered by how the fluid dissipated this energy. All right, I mean it got dissipated, that's all that you care about. But whether it was dissipated by water or nitrogen or sulfur or alcohol doesn't matter. Neither does it matter whether you are pumping it in by some electrical machinery or doing it, stirring it by hand. All that you are interested in knowing is that there is some knowing what. So here is the input, here is the dissipation. So what is going to happen over here? If I am going to input over here and dissipate over there, then obviously the energy has found its way across the scales from here to there. And all that you are seeing is this energy whizzing by, coming from somewhere there and going off somewhere there, and you are simply looking at this energy that is flowing by. And who is responsible for that? This transfer from one scale to another, and this is where these two terms come in. You are no longer integrating them over all space. You are looking at them locally, and locally these chaps are responsible, these two terms over here, which are the same terms as I'll show you in a minute, that these two terms are transferring energy from the scale where you put it in to the adjoining scale, to the adjoining scale, adjoining scale, scale, and so on, and until it's dissipated over there. You sitting over here are happily unconcerned about the mode of entry and the mode of exit, and only see the nonlinear terms at work transferring this energy across you in a tight cascade from one scale to another. That is the so-called Kolmogorov picture. So this local, it's locally transferring from one scale to another. A nice assumption, and Samriddhi will show you that it works sometimes. So n del VR raised to the power n expectation value, Kolmogorov then says that all that it's dependent on depends only on the scale that you are looking at, and epsilon. There is nothing else in the world. So there is only R and there is epsilon, and all the coefficients over here have to be constructed from all these quantities over here have to be constructed from R and epsilon. I do a dimensional analysis and I get that delta V R to the power n. This expectation value is Cn epsilon to the power. So that's just dimensional analysis. On this side is Ln over T to the power n. this is L square over T cubed to the power n by 3, L to the power n by 3, 2n by 3 plus n by 3 is n, T is n. So matches. So that's pure dimensional analysis, and that's what Kolmogorov tells you delta Vr to the power n has to be. But would somebody, I mean, would this be believable? There is no question of Navier-Stokes equation except to say that the nonlinear terms in the Navier-Stokes equation have been instrumental in transferring. But then Kolmogorov did something far stronger. He actually calculated using Navier-Stokes equation delta Vr to the power 3 average and showed that it is minus 4 by 3 epsilon r. So for n equal to 3, it was an actual hard genuine calculation which gave him a result in conformity for this. So there is no wishy-washy thing over here. It's and therefore it's worth actually doing it, which I will tomorrow, provided I can see my way through doing it in, let's say, half an hour. So or less. So that's something that one should see once in one's life. So then, so this is the so-called Kolmogorov's 4/5 law. But what is more famous is Kolmogorov's 5/3 law. So now, what is the 5/3 law got to? Where does the 5/3 law come from? It comes from the energy. So this n equal to 2. N equal to 2 obviously corresponds to the energy which is V alpha by 2. That correlation function, that's what the energy is all about. So instead of integral d3r, that's the total energy. You write it in momentum space as ek dk, and this is the definition. So going from the real space to wave vector space, this is E written as a integral over spatial coordinates. This is E written as an integral over wave numbers or momentum, which I'll use interchangeably. And this is the definition of what is called energy spectrum. And so you can find E has the, this is averaged out. There is 1 over V over here. So it's the total kinetic energy integrated divided by the mass. So the E over here carries the dimension of L square over T square. So this E of k, this has to carry the dimension of L cubed over T square, and E of k is going to be determined by k and epsilon, and if you do the corresponding dimensional analysis, it would be k to the power minus 5/3. Now that's the issue. So this is the 5/3 law, Kolmogorov 5/3 law, E of k. Look at the total energy, look at the energy spectrum. And so this was the one which people focused on very strongly in the 60s and 70s. Then the experimental techniques became stronger, and one started looking at higher values of n. And when you went to things like n equal to 6 or 8 or 10, you started seeing clear-cut deviations from Kolmogorov answers, which get related to the large deviations that Sanjib was talking about. So it does, I mean, there is that aspect of turbulence which does tie up to what, in this respect, to what else you have been learning. So that's for tomorrow. today I'll end so all right, momentum thing. There are two things. One has to, if one needs to manipulate things, one needs to write things in momentum space. Coordinate space is not a very friendly device for doing calculations. So writing things in momentum space is the natural thing to do, number one. Number two, there is everywhere you'll find a word called eddy. So eddy is a word which goes hand in hand with turbulence, and it is the issue is that from large eddy to small eddy, that's the energy transfer. What I said was from large length scales over here, drew a picture like this, and a picture like this to say that large length scale to small length scale over here, that's where the energy transfer occurred. And the more picturesque way of casting it is to talk about going from large eddy to energy being transferred from large eddies to small eddies. But then what in the world is a eddy? So I mean, this is something, while it sounds much better than going from large length scales to small length scales, there has to be, I mean, some meaning behind these qualitative words. So eddy, if you see Landau-Lifshitz, is defined as a typical size over which velocity varies in a significant manner. So it's a size of a size of a blob. Let's say you imagine a blob in physical space, and the velocity across it, if the velocity across it changes significantly, let's say by a factor of half, then that's the size which you characterize as an eddy. The next statement would be that all these eddies, the velocity field is a superposition of eddies all sizes. So now you can have so you want to have some maths going into this. I mean, the vagueness of these things is sometimes a little difficult to handle. So all right, velocity field as a superposition of something or other. What is a way of writing V of RT as a superposition? The natural way is what you have been listening to all through these 5 days. Write a Fourier transform. It's a natural sum. So this is the V of kt e to the power I k dot r. So it's a superposition of these chaps over here. And so now look at this fellow over here. Over what distance does the velocity field change significantly? The distance over which it changes, the change is over 2 pi over k. So that's the change, that's the distance over which this quantity is going to change significantly. Or let's say some pi over k maybe. 2 pi over k becomes periodic, not a great thing to say, pi over k. So what you can talk, if you talk about the eddies, a very natural way is to talk about Fourier transforms, and the Fourier transform and the eddy size, what is called a size of an eddy, is the transform on is the V of k, which has a eddy size L eddy of the order of 1 over k. So you are looking at, when you are looking at these Fourier transforms with k close to 0, that's more or less the mean flow, and that's your large eddy. And looking at very small values of k, those are the small eddies. And so in the wave number space, what is happening over here is this is k large and this is k small. All right. So it's imperative to write things in Fourier space. So maybe, I mean, this is pretty late now. I won't. Maybe you can do this little bit of exercise tonight. The one thing you have to note is the divergence free condition means that del square p over rho is minus del alpha v beta del beta v alpha. So p is just slaved to the velocity field as it must. I have because divergence v equal to 0 does not contain any p, the p has to be determined in terms of v, and that's what happens. So p can be eliminated from there, and this term is a term entirely in terms of v. So all right, great. So you have to write v alpha r is equal to this over here. So v alpha, put it in over here and see what you can manage to come up with. No difficulty over here, obviously, which is v alpha dot k. No problem here either, nu k square v alpha k. It is, I mean, manipulating this chap over here, which is going to require a little bit of work on your part. This one, obviously, as you can see, once you have got this, this is just tied to it, so no difficulty over there. So have a look. I mean, if you can make some headway with this Fourier transform, very good. Otherwise, we'll take a couple of minutes to this. So a good place to stop. Anything that you want to ask about?